Okay,
Yeah.
cool.
All
Uh,
right. Cool.
Today we thought we would talk a little bit about path-dependent types, which is can be one of those like more like intimidating, I think, language features of Scala of like, I mean, you can take it and like people can do just like some like insane stuff with it, which I mean, on the one hand is like really cool that like Scala is like a language that lets us do that. But you know, sometimes it's like that meme of like, you know, you ask whether you could do it, you didn't ask whether you should do it. And so sometimes it can also be used to kind of create things that are like very cryptic and like make us say like, what the heck is going on here? And maybe I should be doing something else. So we're going to try to kind of take it from a more from the beginning, and definitely not going to cover like everything you could possibly do with path dependent types, but are going to try to cover hopefully a couple of like interesting use cases with a little bit of a focus on a couple of places that they're actually being used in ZO 2.0. So if you're watching today, you're going to be kind of ahead of the game for when you start using ZO2. These are generally used in ways that are going to be like very transparent to you, where like something's just going to be cool, as we'll see, and you kind of won't have to like notice how it works unless you want to. But hopefully now you'll kind of have some more tools to see why it works. So, I'm sorry, what's that?
I said I made it. Yay. It took a while.
Yay, yay. So to start out, we'll just do like a little bit of a demo of a. So I'm on the ZO series 2.x branch here. So I've got kind of the latest features in 2.0. And so we'll start off with like a little bit of a demo of one of these features. And so we'll say, and I've got this like Copilot thing. So if you're interested, you can kind of see what that does. My take is it ends up like not being some like amazing thing of like taking like actual code and more just kind of does a little bit like what autocomplete would do of like obvious things that kind of you do. But anyway, maybe that'll make this like slightly interesting as well.
I see it just put a URL in the type signature. I like
Oh
that.
yeah, so some of them are like very silly. Like I think if we like comment this out, like it thinks Zymposium is a tool for creating and editing Z machine games.
My God,
What
what?
that is, but it's kind of like a fun, like I guess if you thought about machine learning, to like
That's
what
incredible.
it comes up with here. I know. Some of them are like, yeah. Anyway, so right now let's just make this ZO1. And I mean, this is where, okay, cool.
Ooh.
And it helps me catch up with you on your fancy IntelliJ tricks, right? So now let me do ZO4, and let me have this be ZO1, and zip with ZO2, and zip with ZO3. And let's take a look at the type of this guy. So maybe audience question here. What's surprising about the type here? And what's different about it than what we get in ZO1? And meanwhile, I can actually even demo another fancy. I'm like trying to catch up with you here. Like, look at that.
Oh, now you have that. All right,
Yeah,
metals.
I
Okay.
can't regenerate yet, but if it's not there, I can generate it.
All right. You're getting closer. I'm being tempted here. Well, I could simulate an audience member, which is to say that in the old version, these would be nested tuples in ZO1, increasingly left nested tuples.
Yeah, that's exactly right. Versus here, if I can add like ZO1 and I can add ZO2 again, and now again I can't quite do your thing and regenerate the type signature, but I can do this, and now I've got 5 things in a tuple, and I've got no nesting. And I think like at a basic level, you can just say like, oh, that's like cool, that's nice. Like that definitely makes it easier for like now I can kind of zip all these things together and I can like map them and do something with them, and I don't need to do all this weird like reassociating of nested tuples. But like, how does that work under the hood? Like you might be asking. And this is one example of where these path-dependent types come in. So if we look at the signature in ZO2, this is actually taking this zippable thing. And zippable is basically telling us what does it mean to combine these two things. And we can see here that we're using this thing, it's a path dependent type here, where the output type of this, it's not just like always a tuple, but it's whatever this zippable.out says it is. And that's kind of really the thing that one of the things we can get from these path dependent types is like the name implies, it means that like the output type can depend on like the specific value that we're giving it. So like if we think about writing a zip function without path dependent types, we could just have something like RE.
All right, IntelliJ Copilot or whatever. Copilot, that was all right. That was all right.
So here, like, and this is what like a normal Scala function would look like. What we get is a tuple of whatever we put in. And it can be like polymorphic in the sense that like A could be any value that we want and B could be any type that we want. But we're always kind of going to get the same structure of a type out of we're always going to get a tuple of A and B. And A and B might be different, but A goes in, B goes in, tuple AB always comes out. And what path dependent types can let us do, one of the like features that they can enable is to let us kind of play with that and not always do the same thing and return different types based on the different inputs that come in. And so we can actually like essentially look at these types and we can say, oh, well, this A here was actually, you know, A and a B, and this was a C. So don't give me like a tuple of the A of this thing. Give me like just take all three things and put them together into one tuple. So that's one of these features that path dependent types enables for us. Let me just undo that so I can get back to compiling again. So we're actually, we'll come back in a little while to work through a little bit of an example of that ourselves to see like what that looks like and to kind of take some of the mystery out of like, wow, that seems like crazy. But before we do that, I want to hit on one other use case of path-dependent types that can be maybe even like a little bit more practical and basic, and it will also kind of introduce just like what are we talking about here. And so the idea of a path-dependent type is, I mean, we can just like start with like a box here is, and maybe we'll have like, we'll have box and we'll have path-dependent box. And so box here is going to take some type A and it's just going to appear as a type parameter. And so this is like what we're probably pretty used to. And some of the things we've talked about before is we probably have some methods here. And depending on, this is a totally random method, doesn't make sense, but it's funny. But depending on what that method is, this may either be covariant or contravariant. And maybe this, I mean, the simplest one would just be this has a value inside it that isn't A, right? And then we might say, okay, well, it's got a covariant annotation there. Or maybe this is a encoder and it takes A values and it encodes them in JSON. That's going to be contravariant. But this is like a pretty normal thing where this A type appears as a type parameter here. So when we talk about path-dependent types, what we're really meaning, like putting aside all this fancy stuff, is just taking that type that was here and putting it in here. And so here we could then have like def value. And the reason sometimes we want to do this is this lets us essentially hide this type information. And whether this makes sense to do can like depend on whether we want to hide that type information. So like here, if what we're really doing is like just a box that contains an A, we probably want to use this encoding. We don't want to use this encoding because we don't want to hide the type information of A. Like the whole point of the box is it's a box that has an int, or it's a box that has a string. And to work with it, we need to know what the value is that's in the box so we can get it out of it. Or if it's a JSON encoder and it encodes, you know, person case classes, then we need to know that it's an encoder of persons and not of some random type. So that's why I think this ends up being kind of like if you didn't think about anything and you just wanted to implement something that had worked on more than one type, this is probably the way you would do it. But this can be useful when you have some type that you're going to use internally, but that the people who are using this whole interface don't necessarily need to know about. So you could imagine something like maybe you have a some kind of like countdown latch here. And you might say the latch is going to have some state that it's going to maintain. Maybe it's going to be like an integer of like just how many we're counting down, but maybe it's going to be some more complex thing that's going to tell us when it's done. So maybe even countdown latch is like too simple a name for it.
Could you briefly expound on what a countdown latch is for those who?
Sure, yeah, and we're gonna hit on that like right now because I'm gonna implement some methods on it that are gonna kind of hopefully elucidate that. So let's imagine that we have some method that kind of, one method is it says like countdown, and let's call it, yeah, maybe let's call it state. So this is like when we want to, so like let's imagine we create the countdown latch and it's going to have like maybe like 10 until like it's done. And then we can call it different times, and every time we call it, we'll like decrement it by 1, and when it gets to 0, it'll do something. That'll be kind of like our like simple example. And so we could imagine like maybe this interface says, okay, you create one of these things by defining some state. So this might be an int. And you define some function that's going to update the state when you implement this. And maybe these actually end up, this maybe ends up just being something that will just be created when we run this, when we define this. And then we'll have some kind of countdown method that maybe is just going to take a UIO of unit. And all this is going to do is it's going to basically update the state for us. And then if the state gets to 0, then we're going to have some other effect that we run when we're done. And so here, like this idea of this path-dependent type could make more sense because for the client of the countdown latch, like in a way, like what the state is that's being maintained internally, like doesn't matter to them. If we had written this interface in a different way, maybe we wouldn't even have this state be an abstract type. For the client's perspective, all they know is like, I can count this thing down and then eventually it'll like run this thing when it's done. But this might maintain an int, it might maintain a long, maybe it maintains some more sophisticated state internally, but we kind of don't need to know about this. And so this is the type of situation where this like path-dependent type can make more sense. And so to do like a little bit more of like a practical example, we're actually moving to an implementation of the schedule type in Zio that uses one of these. And so I think folks may have used schedule before. It's kind of a data type for managing retries or repeats. But the essential idea of a schedule is that it's going to maintain some state internally. and it's going to have an initial value of that state. And then it's going to have this step function that says, like, take one step in evaluating this schedule. And the step is basically going to take an input. So like that might be like if the schedule is like a retry schedule, that input would be like the error we got the last time we were retrying. It takes a state, and then it's going to produce like a tuple of an updated state, this out type. So this could be like how many times the schedule's repeated, or like how long the schedule's been going, basically any information we wanted to output. And then it's going to also produce this thing that, let's just call it a decision. And that's just going to be a sealed trait where we're either done or we're going to continue after some delay. And maybe right now we'll just do that as a duration. Compiling. Does this make sense so far? Does anyone have questions on this?
A couple are happening in the Discord. How does your VS know? It's mostly GitHub Copilot things. So.
I know, it's kind of a fun thing. I figured that might be like a little conversation starter.
How does your VS Code know what you're going to type? Yeah, it was pretty good there. The 2.0.
Yeah, it's not bad. So let's think for a minute of why we might want to make this a path-dependent type, because we don't have to. So let's just see for a sec why we don't have to. Like, we could write it like this, and we see this like compiles just fine. So this is a perfectly like valid way to write it, but why would we want to write it one way versus the other? Well, so one reason is we can see here that the state type is invariant because it appears both as an input here and as an output here and here. And one of the things we talked about before is that having invariant type parameters, if we can avoid them, is generally going to improve type inference for us. And we talked about this idea that maybe we could try to kind of split if we saw that, we could try to split it out into like two different type parameters, but it's not really obvious like how we would do that here. And it does kind of seem like the idea of the schedule is it kind of just has one state type that it like keeps updating that type versus kind of taking in one state type and like taking out another state type. And then the other thing about this is like even putting aside the variance issue, it feels a little bit like this way we're exposing an implementation detail of like most, if any of you have like worked with schedule, like it doesn't have this state type parameter right now. And you've probably like you've never felt like your life was worse for not having that state type parameter. Because you can imagine some of these schedules, like what this actual state type is could end up being like some pretty complex thing when we have this schedule that's like supposed to do this like window of like it's supposed to like recur every 10 seconds, but like if it falls behind, then it's not supposed to allow the recurrences to pile up. And maybe we're also only supposed to do this like 5 times. And like that schedule, like whatever that state type is that we're like maintaining, like could end up having a bunch of stuff in it. And like, we don't necessarily like need to know what that is to work with the schedule. So both of those factors point us a little bit towards this being a more natural implementation. And so like, I think if you're thinking like things to take away from this, I think first like simplest thing to take away is like, there's this like, you can have this type inside of the data type you're defining instead of as a type parameter, and that's called a path-dependent type. And this situation of where you kind of want to have the type, you want to maintain this type information here, so you like know that like this is the same as this is the same as this, but you don't necessarily want people outside to know it. that's like a good time to think about having this like type here. Does that make sense to folks?
I think so. Yeah, I'm curious personally, like how do these, maybe you're going to get into this. Feel free to say if you will later, or to, it's not important, but how are these composed in the same way, right? So when we write combinators, we'd like to sort of, either tuple up or either up the inputs, right? If we zip two schedules together, maybe we're going to get a tuple of the outputs, maybe we're going to use that zippable type to generate something with the two outputs. How are these states going to be sort of intelligently composed when you combine schedules? Would you want that to happen even?
Yeah, so great question. I think almost before we get there, there's like a thing we got to point out that I think I briefly hit on, but I just want to like kind of, I guess, emphasize here. So let's say we like go to the box here, and let's say I make this box path dependent. So I say this type A goes here, and then I make a constructor for my box. And so this will be like new box, and I'll call this A0 just so I don't have like name conflicts. And we'll say type A equals A0 and val value equals A. So this is all fine, but watch what happens here. And this is kind of both the advantage and the disadvantage. Is if we look at the types of these, both of these are just boxes, which is nice if this is like, if the thing inside is a detail that I'm kind of trying to hide, but can be a problem if people need to actually work with that. Because like I might do, like you might think I could do something like 2 is box.value plus box.value, because we know the value in this box is 1. But Scala compiler says no way, because I haven't, outside, we haven't made that information visible, that like this type inside the box is an int. As far as outside the box, we know like it's just some value. So like this is actually trying to do the like string concatenation like plus, and not doing that. So again, like that, in a way, it's like the feature and the bug of like, if we want to hide it, then it's great for hiding it. And in some cases, it's really nice because it means that like, if I'm going to have a bunch of these boxes, I don't have some issue of like types being inferred as any or something like that. But if I want to do things with the boxes that rely on that type, I'm going to have issues unless I kind of do some like special stuff to get that to work. So yeah, I think that's probably a nice opportunity to start to go to the zippable example. And I'm actually going to try to build for us something that's a little bit similar to that. But what we're going to see is that whenever we want to, we can, so if I'm implementing operators here, I can always combine these things. So like, let's just go to like the box example. If I want to, I can do, let's call it like a tuple box. And so that's going to take this box, and it's going to take this thing in this box, and it's going to give me a new box. And so here, that's not quite right, but again, admirable effort from Microsoft or GitHub here. So here, the A type is going to be a tuple of the self.a and that.a. And value is going to be self.value, that.value. And so we see we can refer to these types here. It's just outside of this, we don't know what they are. So like I can do like, equal to box, tuple box, box. And so this is like totally like valid code, and like this is a real box. And I mean, if I want to, maybe let me just like prove myself by doing something like print contents. And so I can take that tuple box, and then I can do like tuple box dot print context, and let me scale it on now. And yes, it is bad to do nullary side affecting methods. I'll agree with that. I'll try to follow that advice. And so now if I run this, and so it totally like inside it knows that like I was able to put these two things together. It knows them, and I can even put two different things together. But outside of the box, I'm not like able to use those things. So the way that I can try to recapture that if I want to is I can use this additional type here, a refinement type. And so here I could do, maybe I'll call it like with state. And that's going to take the same type parameters I had originally, but now it's going to have one other type parameter. And this is going to be schedule. And first, I'm still just going to fill in all the same type parameters that I had before. And in out. And then here, I get to specify what that type is. So I could say type state is equal to state 0. And so this is now a schedule that knows that the state type is state 0. Or if I wanted to here, just because this will be like a little bit easier just for us to like demo, I could say type, maybe I'll call it with contents, A is equal to box, type A, and again, I need to avoid these little name conflicts. So usually like doing the 0 is like an easy way to solve that. So now if I wanted to, I could always return the more specific type here. So here I can say box with contents A0. And then, so now these things know that the value inside is an int or a string. And what can be a little bit nice about that is it gives me the ability to control when I keep and when I forget, or when I hide the type information, which again is like the feature and the bug of using this. So like here, if I just had like my box and my box 2, I know that these are ints and strings. And so like now, if I do box dot, and look here, box dot value int. And I could do like box dot value int plus box dot value. And now this is totally fine. This knows it's an int. But if let's go to like that tuple box. So the tuple box, even though it's a box of a box with ints and box with strings, the tuple box has like forgotten what the contents are. And again, depending on what I'm doing, that could be a good or a bad thing. So if I like that, then great, I can just leave it as is. If I want to, I could do this be box with contents too. And then here, I could say that the contents of this box are going to be self.a and that.a. And so now my tuple box is a box with an in and a string. And
I think one of the interesting things about that is that you did not have to annotate like the that. You still took a box, it was still defined in a box, but you didn't have to accept a box with contents. Just kind of all worked out that way.
Yeah, exactly. And that's going to be kind of the key like enabler for like the next set of things we're going to do, because this is letting us say that like you just put in a box, and based on the value of that particular box, I'm going to decide what output to do. And in this case, we're not really doing anything exciting with it because we're just always doing the like A inside the box. But this is basically the feature that's going to enable us to do like this zippable type thing, because it's going to allow us to like look at this type and decide like, oh, based on its value, we wanted the output type to be this or this other thing.
I'm not sure if you mentioned, oh, could you go about, I'm not sure if you mentioned this before already, but if anyone was wondering why these were called path-dependent types, it's because of this. You're sort of nesting into the path. Yes, the type is inside of some path, some dot-chained path that's dependent on the value.
Yeah, and I think to build on that, the other really is the A is dependent on like this specific box. So like the other thing I could always do is I could do like object box, and then I could do like type A. And so this is, well, I guess not.
I think you may also have an object box below the companion.
Oh, I probably do. All right, so let me call box one. So here I could always do like box1.a, but now this A is like a static type because there's only ever one box one, right? It's just an object. And so there's just one A. Versus the neat thing are these path dependent types is like every individual box we create has its own A inside it. And so the A depends on like the particular box, not just boxes in general. So I think with that information, with that kind of setup, we're ready to try to do like a little bit of like an exercise that tries to get us to something like this zippable thing. But before we do that, maybe does anyone have questions before we push forward?
I did miss one before, which Vanshav asked if schedule could be implemented using zpure, I think, because yeah, the types do sort of look similar, at least this encoding.
I think it probably could. I think one of the reasons that I think it probably will not be, just because it's kind of, I think we're trying to do some specialized things with the schedule that are kind of enabled by having like a more narrowly constrained data type. But I think it definitely, I mean, you can see it's like kind of a state transition function. I think it could in principle be. Part of the reason that we're actually moving to this encoding is we want to be able to support serializing the state of these schedules. And we previously had an encoding where like the state was more implicit. So like the step function just kind of gave you back a new like recursive thing. And there wasn't really a way to like actually like get at like, oh, the state is this like one thing here that like I could get at and I could like serialize or deserialize. And that becomes important for things like ZeoFlow that we talked about last week, where we potentially want to have these schedules being used to like retry things on different nodes. And if a node goes down, we want it to be able to kind of load its state and continue with the schedule. And so we need to be able to serialize and deserialize the state. And I think that's also a nice example of this idea of kind of selectively hiding and showing information, because it's really nice to keep this basic schedule type like this, where it just has these three type parameters. So like, if you don't want to, you kind of don't have to care about that state. But then in some cases, we do want to like retain that information on the state, because if we're going to like serialize this thing, we've got to kind of know what that actual state type is so that we can like find the right encoder or decoder to use for it. So I think nice example there. Yeah, anything else before we push forward?
Yes, one other one just came in from Dom. Wouldn't that mean that we might end up with two strict types? Like when you make constants in Scala, you have final val my constant equals the string blah, but then that type is actually not string, but now more specific, like the actual singleton type, of this the string blah at the type level. Yeah, that sometimes happens. I'm not sure if yeah, perhaps it does. I think there's some details depending. Sometimes if you like extend that singleton type thing, it'll make it more constrained. But yeah, does this cause problems potentially where things get overly constrained? I think is the question.
So generally not, and I would say especially not with the singleton types, because I think at least in the work I've done with them, they really have to you have to kind of work to tell it you want the singleton type. Like if you just give it a string, unless I literally put the string in the type parameter brackets, it'll kind of just give me back a string. It won't give me back this type of singleton type of atom. I think the thing you more commonly see here is that issue of you kind of forget the types, because one of the, I guess, again, the good and the bad of these refinements is I can always forget a refinement. So anytime I've got a schedule like this, I could just forget this information, and that's valid code. And it's also kind of easy even accidentally to do that of let's say I've got this tuple box, and so I'm really proud of myself. I've got this type information here, and then I'm just val tuple box 2 box equals tuple box, and then I say val tuple box 3 equals tuple box 2, and then I want to do tuple box 3 dot value. And suddenly, I've totally forgotten it. If I look at this type here, this is just this dot A. I got no idea what it is, even though I know looking at it that all these things are the same type, because I included this line here where I kind of forgot that information. So challenge of the refinements is usually we forget the refinement, and then we can't use some information that we want to use later. Okay. So with that setup, I want to show how we can kind of put those tools together to do something a little bit fancier, like the zippable thing we saw at the beginning. But we won't do the actual zippable because I want to show something a little bit new. So I thought an interesting use case we could have would be unifying nested iders. So the zippable, I think, ends up being more common and is kind of the tuple case of we've got an A and a B. But we could also imagine we've got some cases of we've got various iders. So we could say, and maybe I'm just gonna, maybe I'll make a little domain here. So maybe we say error, and then we have password, and maybe so basically we'll have some domain. We could have a much larger set of errors, but right now we're going to kind of say we're going to get some information, and we're going to either we can't decrypt it or we can, but the password is invalid, and those are kind of the two ways that we can fail. And maybe if we want to, we can add some more of these. But so basically our problem is going to be if we've got something that's an invalid password or could decrypt, I want to just collapse that either down into the most specific type possible that I could get. So here I would want to return a domain error because that's kind of the narrowest way possible that I could unify these two types. And we could imagine that I wanted this to work also with maybe some more complex types. So if it's if I accidentally create some like nested thing that's like either an invalid password or I could not decrypt or a invalid password, yep. Then I also want to be able to flatten that down into like a single value. And so basically like what I'm going to end up wanting to implement is something that like maybe we'll call it like unify. And so what this is, we don't really know yet. But basically we're going to want to be able to do we're going to want to be able to do that. So we're going to want to be able to feed into it like a potentially like nested either and just collapse all the types into like the common supertype of whichever one of these values actually exists. Does that make sense as kind of a scope for us to explore here?
Yeah, that's interesting. I mean, I'm curious if maybe we'll run into problems with this one, right? Like if, what if on the right-hand side, it's an int or something? Should it be unified to, you know, the least upper bound might be any in that case?
Yeah, I mean, I think that's kind of what we would be saying. I mean, we could maybe try to like do fancier stuff to like prohibit that from working at all. But I think like the initial might be like, just like if we have a ZO and we have like two different errors that are totally unrelated, we're going to get any or object. And, you know, that's just, that is the kind of closest super type. And probably that's going to cause an error for us pretty soon. And we're going to kind of realize like, oh, that wasn't what we wanted. It isn't going to match our type signature. But yeah, I think at least first pass, we're going to say we're just going to unify to whatever the super type is. Hopefully it'll be narrow. Maybe it won't be narrow.
Sounds good.
Okay. So the first step in this is usually taking this like ultimate signature we want to make and expressing it in terms of some path dependent type. And since we're just starting out, we'll kind of be a little bit iterative here. We'll like be relying on making up things that like don't really exist yet. But so we might say this unify method should take an input and so this input could potentially be anything at this point. And then a really good approach for some of these problems is just like we had that zippable thing, to create this additional data type that basically describes the logic of like this kind of type level function that we want to do of like, when we get an in, like we're going to look at it. And if it's this in, we should do this thing with it. If we get this other thing, we're going to get this thing with it. So here, maybe we call it unify or maybe we call it union. So union is going to be a union. Awesome. This is like the better version of like the Kit is like the perfect like Copilot. And so this union is going to need to know what this input type is because we're going to like use that information to decide what the output type is. So I'm going to parameterize the union on that in type. And then the out type here is going to be one of these path dependent types. And so here I'll do like union.out, again, kind of following the like making up things that don't exist yet. So now I've got this union thing that's basically going to build in the logic for getting from this input type to the output type. And so I can implement different instances of this to describe essentially like different strategies for going from inputs to outputs.
And I think the key here is also that this would be implicit,
yeah.
Right?
Exactly. Yeah. And yeah, so right now we're missing the instances to make this work, but we kind of have like the very basic machinery in place here. So now let's try to kind of implement one of these. Yeah, exactly. And so this, and so one of the things we're going to want to do here, and usually like a good practice when you have these path-dependent types, is to start off implementing that like refinement type. So in some places that's also called the ox pattern. I feel like that's like a little bit of like obscurantist of like kind of doesn't really like tell you what it is. I mean, I guess kind of auxiliary information or something, but we've kind of been using this pattern of like without or with state, which I feel like is like pretty like intuitive. So I'm going to try to roll with that here. And so the way this works is we're always going to take our initial, and then we're also going to take the one that we had as the path dependent type. And I've just done this enough times that like you kind of need to add the 0 afterwards because we're going to use it here. And then, yep, that's right.
Oh, wow.
Yeah, that was nice, right? And I'm also going to do one more thing here, and I'm going to make this contravariant because this is like the input to this. So this is kind of saying like, hey, give me this, and I can stick out. And I'm going to also give myself a method here. And so this just says, give me the input and I'll turn it into the output. So now we've got kind of the, let's see. Oh, yeah, right.
That's me hitting save obsessively.
Yeah, no, it's good things. I just want to, those are the expected errors, yeah. So let's try to implement an instance of this. So as Kit said, we typically want this to be implicit because the ultimate experience we want for like users, we just want them to call like unify on this either thing. We don't want them to actually like have this thing. We just want this to be automatically found. And so we've got to make these values here also be implicit. And so maybe the first one I will call like union either. And this is going to take an A. And it's going to give me this union dot without. And this is where like it's important to use that type because I'm going to want to retain that information on like what the out type is that this is producing here. And so this is going to take as an input an A and an A, and it's going to give us an output back. And I'm taking advantage a little bit of the fact that I'm making this contravariant here, because that's going to kind of get the compiler to like widen the type to be like the narrowest A value that unifies these things. So let's see what this might look like. So I'm just going to do a new union. And since I've already specified the refinement type here, I don't need to specify it down here. So this will just be an either AA. And then the out type is going to be A, which is right. And then to implement it, I need to implement this method, which that's an interesting implementation. That's not, I don't think the right implementation. Anyone have a suggestion for how we can implement this?
Oh boy, pick me. Pick me. Oh, I know, Dom got it. Yeah, well, Dom has a solution. In.fold, I think.
Yeah, we got to in.fold like identity, or I think on at least Scala 13, there's an in.merge that'll merge them to their common supertypes.
Basically does the same exact thing though.
So the exact same thing. So what we may not have noticed here is we went from having 2 compilation errors to 1. So if I just comment that one out, like this example is working now. So we can, I'm just going to move these down here so it's easier to see kind of samples along with the results.
Nice.
But so we've already been able to kind of take this thing and just get out the domain error. And so far, I mean, you might say like, oh, this isn't like, you could have just implemented this without using any of this fancy stuff of just like, def unify in either, A, either.merge. So that's like, we still have more to do, but like, okay, first step here. And then what we essentially do is like we have the ability to just implement more of these implicits. And some of this like relies a little bit on kind of the rules about like how the resolution for these works. But a trick that ends up being pretty useful here is if you define another trait here. So like I'll call this union low priority. And then we have the original one extend that. So now the compiler is kind of it's gonna look for us for this one before it looks for any instance I define here. And if I want to, I can even like, I can have more layers of this. Like if I want, I could do like union low priority 2. And then this could be like union low priority 1. And then this extends union low priority 1. And so now like the compiler is first gonna look here, and then gonna look here, and then gonna look here. And that ends up being like, oftentimes like pretty important for implementing this, because like what we essentially want is we want to have a set of like rules for like how the compiler is going to go about like trying to simplify these types. And we're going to want them to be done in like a particular order. Because like say this one here, like if it's just either, if it's just one either with no layers of nesting, then like this is like the right solution that we want. And so like this is working for us. This is giving us a domain error. This one here, if we look at what it's giving us an object right now. And the reason it's doing that is because this is firing once, and it's trying to unify the left that's the left that's an invalid password with a right that's an either. And the union of the invalid password and the either is basically an object or any, because those are like two completely unrelated types. So it's kind of like, I mean, it's doing what we've told it to do so far, but it's just like not getting the right answer. So what we could do here, if we want to like handle this case, is we could say, okay, let's implement another instance of this. And maybe, so like we could kind of say, well, like the problem here is that we were kind of set up to work with just like a simple either. We're not set up to work with this like nested either on the right. So maybe we'll call this one like union either right. And then this one will take a either that's nested like that. And so then I'll just like carry that through everywhere. Out type is still A. So now this becomes an either AA. And so now, Dom Noren, that's his day in the sun of now this will be something like fold, and then we can merge this guy. And so now we kind of run into the problem that I was just like, evidently setting us up for a little bit of this one now is kind of the right solution we want for this second one. But we're running into a problem because both of these could theoretically be like valid solutions of like, it is this nested either on the right, but it's also just an either with two things in it. So right now, both of those are like trying to like apply, and because they conflict with each other, the compiler is just blowing up. But we can now use this little trick we set up for ourselves, and we can move this into one of these lower priority instances.
Nice.
And now we got it. And we can imagine that so like this is all, I mean, this is pretty cool. I mean, I'm not gonna change the world, but this is pretty cool. Now, there's still definitely things we haven't handled. Like so let's just set ourselves to blow up here the other way. So I can say I want to make it like that. Down. Okay. And so now I could say, well, look, if this is like an actual thing that like we want to expose to our users, then it should definitely work if we switch the order around. And right now it's not, because we haven't kind of set ourselves up to do this. And yep, Kid is already one step ahead if he's doing the same thing on the other side.
Woo! Take that, GitHub. My job. All right.
And now this is working. And now we could, so let's even like press a little bit farther, and I could say, well, boy, it should work if it's on either side, right? So this should be okay. And we'll, I have a feeling, yep. Okay, so he's implementing an even crazier one that is not like where we are yet. But so we'll, yeah, so let's implement another one, and we'll call this union, maybe we'll call this like union either both. And so this will just do the same thing here. Oh, I'm not sure it's that, sorry. It's not good. But this is what I want. This, and then this merge. Okay. And now we've got kind of the same problem we had before, where we've got conflicting ones here, because basically this either both could fire or the left or the right, because these are both kind of, this is like a more specific case. So we just use the same solution we did before, and we'll kind of push everything up one level in our little priorities here. So we'll say the kind of lowest priority fallback thing is if it's just a simple either and you can't, there's nothing else that applies, then just unify those two. If, oops, bring these down here, and then we'll leave this up here. So now we're basically saying, first thing to try is see if it's like nested on both sides. If so, handle that. Otherwise, see if it's nested on one side or the other. Otherwise, just handle the simple case. And now all of these work. So there's some limit to this approach of like, if we have like 10 layers of nesting, and there are a lot of different ways we could kind of nest these things, like, at least this example, we can definitely like get this to blow up. But we could also see like, maybe at some point we say like, look, we're good with supporting up to like 3 layers of nested items. We don't think people are gonna be creating that many. And like, this could be like a nice little thing for us to like essentially like smash through these like nested data types and like give us something back and kind of simplify what would otherwise maybe be a bunch of like folding and merging. So that's kind of the like the approach here. There's like a fancier, an even fancier version of this we can do is we can try to recursively derive these. So we could imagine that like we essentially say, well, like, look, if I've got an either of 2 things and I'm able to like unify each of those 2 things, then I'm able to like unify all of this. And that in a way, like if you can do it for your problem is like the nicest way, because like if we could do that, then we could just do like any arbitrary structure of eithers. At least in the playing that I've done, I haven't been able to get that to work inductively. I think there's some limits in Scala 2 with implicit resolution for contravariant types and type inference there. So it seemed like we kind of ran into that a little bit, where like when you try to do this, like this thing kind of relies on widening these types, right? So like when I have the invalid password or could not decrypt, like this relies on widening them both up to the domain error. And it seems like that doesn't trigger when we try to do this inductively. So this may be a particular one where at least with the limits of the language, the limits of the tricks I've tried so far. We can't do it in like its like full generality, but you can see how like even like having something like this, I mean, hopefully you're not like, this is already probably pretty painful to create to begin with. And in fact, this is pretty similar to like the way that like that zippable thing is implemented. You can do a very similar thing if you just have like different cases of if you essentially say like, well, you know, if I've got a tuple 3 and I add one thing, then I make it a tuple 4. If I've got a tuple 4 and I add one thing, then make it a tuple 5. And so you can, it's kind of a cool thing where you can implement this like very specific logic of like how the input types drive the output types. And again, it's one of those things where like you got to like use the power wisely of like, you could do this to have like totally crazy things of like, you know, if you get an int, then like give a string. And if you get a list, then give a Boolean. And like, people are gonna be like, what the hell is going on here? But I think if you kind of use it in like small doses, it can be pretty nice. And so
yeah, that's interesting. I thought maybe you were going to the recursive definition, but that's interesting. I think I can see maybe why that wouldn't work here. But yeah, that seems like maybe that could be a redemption arc some other week if we can figure that out.
Yeah, it's definitely kind of the interesting way to go. But yeah, I don't know if it quite works here.
Yeah.
You can see this is all one of these things where we're like pushing the type system a little bit to kind of try to deliver a nicer API. And sometimes we kind of get all the way there and sometimes we get part of the way there.
Yeah.
So another like case where something like this shows up is those of you who have maybe either played with Z02 or looked at the release notes. There's this new operator called zo.from.
Oh, by the way, real quick,
okay.
I will be right back just to let you know. I'll be right back just in 2 minutes.
All right. Well, I was going to ask people for questions, but people have to, I guess, wait until Kit is there.
Suspense. Load them up.
So in zo2, there is this new operator called zo.from. And so I could do like from either one. And take a look at the type here. So we put in an either, and it took the left value and it put it on the error channel, and it took the right value and it put it in the success channel. Now, in this case, this was kind of our like toy example where these were both failures, but typically if we've got an either, you know, we've got something like val my either is equal to, and maybe this is either like a string error or like an int value. And so when I do zo from either, my either, generate this type again. So this is going to give me a zo that succeeds with that value type and fails with that error type. And one of the kind of fun things with this is we can have lots of different data types. So we could do like an option, list of ints. Oops. And we could say val zo2 is equal zo dot from my option. Oh, I think I did. Oh, I already. Where did I define zo2? Oh, yeah. Okay. Maybe I'll use higher numbers here. I'll use 0, 10, and 11. And so if we look at the type of this, so again, it took the option, it extracted the list out and put that in the success channel. And in this case, typically when you're working with optional values, this could be unit because the option has no information for why it failed. But typically when you're working with options, a lot of times it's actually nicer to compose if you have an option of nothing here, because then if you have other optional values that do have an error, they all compose together nicely. So like it gives you that. And this works with like lots of different things. So if you have like a future, it'll give you a zo from a future. If you and there are also variants for like managed values and for streams. So it's another kind of nice example of this pattern of like, if you know Zio really well, you don't need this. But if you're just getting started, like a really common question I get asked is like, how do I make a Zio from X? And usually my answer is just, it's probably from X. But say even that, like you don't even need the from X, you can just do from. And most of the time, this will kind of get the right thing for you. So this is what we're calling like a smart constructor of. We're trying to use logic like what we implemented here to automatically generate the right Zio type from this value.
I'm back, and we did have one question.
Yeah.
Which is, I think for this, Don was asking if it was able to figure this out. I think you inserted these using that that new trick, right? But even if you have
oh yeah, you're wondering like I'm not like just tricking you by specifying.
Sleeve. What's up your sleeve?
Yeah. Yep. So let's get rid of those. And then one, if we hover over, we can see it. But two, if we kind of don't trust our IDE, which sometimes we don't, the other way I like to test this is have one version where you don't specify it. So here, this is like unaided type inference, you could say. And then below that, you do something like result 5, domain error equals result 4. And so now this will blow up if these types don't match. But I was not playing a trick by specifying the types there. I was just kind of using that to check myself. So yes, these without clues are getting the right type. And that's actually one of the nice things about this pattern is like, there are other ways you can try to do something similar. Like, I mean, you could say like, hey, why did we do any of this? Like, why don't we just have 4 different overloads of unify? And that will typically it'll typically have worse type inference. It'll run into these conflicts because you're not really able to prioritize them. Versus this, like when you get it to work with the implicits, the type inference is pretty flawless. Like sometimes it may work, like we saw, like if we create like the super complex one with like 10 layers of nesting, like it's not going to work just because like we don't have the implicit logic set up for like the compiler to do the right computations to get us there. But if we've got that working, like this is like really spot on in terms of type inference. Like, you know, there are some things that sometimes have issues. I don't think I've ever seen an issue where like the implicit resolution worked right and you didn't get the expected type.
Cool. I mean, that's all the questions.
Cool. So I think that's that's probably at least what I had to share on path-dependent types. Would definitely like open it up to anyone who has like questions or things we want to explore, or if we want to, we can kind of play with one of these examples more.
Yeah, that's awesome. I mean, it's nice to have the this is our record time, but short and sweet. I mean, 70 minutes and sweet. Still pretty good. Yeah, I mean, it would be interesting to maybe peek at the Zio from implementation just to see one that does have that sort of recursive nature to it that we explicitly did not use to this.
Yeah, well, so it's interesting. That one also does not use the explicit, the recursive.
Oh, really? Okay, interesting.
Yeah. So we've done some explorations. Actually, something I'm kind of actively working on of kind of being able to support. Like you could imagine, you know, you want to do Zio dot from either this guy, and right now it'll work. It just won't kind of give you the most specific type here. So like here, it basically smashes through the first level. So it says, okay, I got an either, and this was the right, and this was the left. And it takes that right side and it puts it in there. Which, I mean, to be fair, maybe sometimes you do want to succeed with an either. So, you know, that's kind of like one of the challenges here of like, you got to like figure out how to be smart, but not too smart. So like, I mean, this is definitely going to be helpful. And to be fair, this is like probably a unusual case. But that's another one where, again, we're kind of like pushing the particularly in Scala 2, some of the limitations here, because what we really want to be able to express when we like do some of these unions is we want to be able to do like the union type, the two errors. And we don't actually have union types in Scala 2. We can kind of play with them with poor man's union types like this, but they don't quite work as well as the real thing. So that may be something that is coming in the future. Yeah, it's kind of just follows a very similar pattern to this, which I think is a little bit maybe like less exciting, but also like just very like solid and just works.
I did have one potential idea because Vanchev asked about, well, said, yeah, induction would be nice. And I think it might be nice to explore maybe in a little constrained way. I had one sort of thought of maybe like just also to get some muscle memory in there of this pattern as well.
Yeah.
One fun thing to do might be to have like a trait called add A and B with some kind of type type out, and we can probably give it some to follow that same pattern. I will use here. I do like that because yeah, you will often see aux, but that's just aux for everything, and it just kind of is confusing to people. Like, what does that mean? Auxiliary, what? So yes, it really means yes, it's specifying those nested types exactly as you said. So AB out 0 equals type. Oh, sorry. Add AB type out equals out 0. And then I think we will need some kind of extends low priority, add low priority. And then implicit val, any add. Oh, actually, maybe this is interesting. So, well, yeah, let's make it silly down here.
Yeah,
so
the most general ones, you want to be like the lowest priority. You want to start with the most specific ones.
Yeah. So let's say any add. Yeah, I probably should have done something slightly different here, but it's fine. So if we have no rules for it, let's say, if we have no more rules, we will make ourselves a new add from AB, if it's the most generic thing in the world, and type out will be the, oh, this has to be a type, actually. What am I?
Well, I mean, what if we think, I mean, we could make one, maybe we'll add all the values in a nested tuple?
Yes. I think so. I think that makes sense. I was trying to think of like actually doing like
yeah,
using some kind of integer value, but that's I realized I was I got excited before I thought this.
Well, yeah. Well, I mean, we could probably do one where we just do like the cardinality of a tuple.
Yeah, that would be cool. That would be cool.
Like the size of a tuple.
Yeah, I'd like that. The size of a nested tuple.
Yeah. All right. So why don't we do that? So, yeah, this would be a fun exercise to try to work through. So I guess this one in a way is going to be a little bit simpler because so here I wonder if there's going to be two because this one we're not really going to need an out type. Right?
Yeah, because it's always going to get us some.
So this is just kind of going to be more like playing.
I suppose that's not a type level thing. So that was.
Well, no, I mean, I think it is a type level thing. It's just like, it's just kind of an implicit thing. Like here, we're kind of using the combination of like implicits and path-dependent types. And yeah, I guess the size one is
We could do this. Okay, and this is actually nice because this will be very, very simplified as well. So if we're at the end of the world, we can have the size just return 1, right? Because it's kind of just some number. This is something that's basically not a tuple anymore. It's just some value because we're going to handle the tuple case elsewhere.
I think this is going to be pretty straightforward, yeah. But yeah, so. And so here.
Now we might need some multiple low priorities. So.
Yeah, I think this one may be pretty simple, but let's see. First. A. And this will be AB, and so that'll be sign.
Yeah, perhaps we won't need multiple levels. Yeah, let me
I think this one we should. Yeah, let's make a little test for ourselves here. Play with some inductive
size examples. So we'll have just first like
Oh, and we should just make a helper method for ourselves here, I guess. Def size in and in.
Okay, so let us see. Oops, there's some missing closing brace down here. And then I think, is everything else happy? Missing closing brace. Oh, did I? Yeah, let me close that up there.
Yeah.
Oh. New size, it takes parameters. This would be the tuple AB. I think then we're almost good. Size, and size doesn't even actually take parameters because it's the one it's been just sort of implicitly resolved, which is cool. So it's a size dot size.
Yeah, we're kind of yeah, we're playing with different things here.
Yes, yeah, and potentially we don't even need the argument either. That's the nice thing. Yeah, it could be convenient if you want to get the size of an argument.
Yeah, another interesting thing we could do is I think we could make this a path dependent type, and we could compute at the type level the size of these. But maybe let's do this first.
Yeah.
I think we had another.
Yeah, I'll add a print line down here. So print line, and then we'll say, or maybe we could even just do pure print line size so we can see it. So in goes to size. And is that stat? Oh yeah, because that returns a unit. And perfect. Okay, so let's do size A, size B. Those should both be 1, right? A, B should be 2. Yeah, can we recompile this with running the size examples?
Yeah. So let's see.
Oh, is it? Oh, good. So yeah, all right, we got 2 already. So let's now do ABC.
Yep. Yeah, when you can get the inductive to work.
Well, not quite. And I wonder if this is because, yeah, this is not nested tuple. This is a threeple, which we did not quite cover. However, if we do AB on one side and C on the other, then we do get 3. So we've gotten it to be inductive this way. So I could do AB. So AB, and then if I do AB, okay. And then if I do this on one side and that on the other, we'll see that it's 6, right? Yeah. And so on and so forth, which is pretty cool. And the nice thing is that this is totally done at compile time. It's building up. Well, it's sort of doing what GitHub Copilot does for you, right? Where it's if we scroll up to the inductive definition, right? It's first looking for a size of the thing on the left and a size for the thing on the right, which is then going to sort of kick off this breadth or depth first search. Doesn't really matter, not sure how it's implemented. Probably breadth first search so that it doesn't sort of like go forever in one direction, but it's going to eventually find this base case, which applies to literally anything, which is important to make this the low priority version. And it'll get you that back out. So it'll feel a lot like writing inductive recursive functions, except sometimes at the type level. And in this case, it's not fully a type level function. We didn't use it to have the output type depend on this, but we had the implementation depend recursively, which, you know, we could have implemented this purely at the value level without using this trick, but to sort of minify just this trick of implicitly relying upon a recursive definition, the sub-solution really, which is why this will look a lot like having a base case in the low priority and then having the recursive case in the companion object that will rely on sub-solutions. So you could probably write out actually like translations between what this looks like using this implicit method versus the a normal sort of value level, term level programming as we're used to, and see some similarities there in recursive functions. But yeah, that's kind of how that trick would work. And you can see how we might use this with the either code before to create cases that could nest infinitely or until whatever the compiler stack blows up in terms of either's towards one side or the other. So you don't have to implement, you know, a million cases.
Yeah. And some of this you can also see here are like one of the nice things in Scala 3 is they're moving to this like encoding where like the tuple is like always itself a recursive structure. So like then we could kind of just implement this in a very nice way. Like here, to kind of get the examples where they're not pairs to work, we could create some other like inductive definitions where like we kind of say, well, like if it's a tuple 3, then remake it into a 1 plus a tuple 2, and then the other one would fire and everything would kind of work for us, but like we'd have to work for a little bit more. So like, that's kind of one thing that's coming in Scout 3 that's nice. If we like really wanted to go down this road, like you could like think about like defining like like the kind of natural numbers at the type level, and then you could kind of actually have this be like a fully type level thing that like at the type level tells you the size of it. But like, yeah, I think there's a little bit of a, I mean, sometimes it can be really cool, but there's definitely like, how far do you like want to go here where like, I think some of the stuff we talked about earlier, like is just like has very like practical benefits of like, okay, like your code's just going to be like nicer when you do this thing because like this is just going to work for you, versus I think some of the stuff can be just like, I mean, really like intellectually interesting and like fun exercises, but have a little bit less like practical application in at least most cases.
Yeah, but it's fun. It's fun to wrap your way around, and it might help you understand some of the crazy looking code because it's definitely, there are patterns that you can extend here. But the first time you see it, it can be incredibly overwhelming, especially if it's like you see awks and you see all of these different implicit definitions and like traits extending other traits, and like where's the function? What's happening? How is this working? But when you sort of see it as just sort of a recursive function that's kind of spread out awkwardly amongst a stretch of syntax, it becomes a little easier to read. So I hope, if nothing else, maybe this presentation could help you understand the crazy code and have more of a bearing. If you want to like jump into the Zio code base and see what Adam did with the smart constructors, I think now you probably can figure out most of it. It's generally not even that complicated. It just has all this kind of scary boilerplate around it.
Yeah, hopefully I see it's actually not even so scary. Yeah.
Yep. So we have one last question here so far, which is, could we implement H lists with these path dependent types? And if we could, would it make sense? So I don't know, we've talked about H lists here before yet, but we can mention maybe what those are, and could we implement them with path dependent types?
Yeah, so I think maybe at some point we may have to at least space out the type wizardry with other stuff here, but we could definitely, I think, do a session on them at some point and kind of maybe explore kind of different ways to do that and different operations we could define there. But yeah, that could be fun to play with sometime.
Yeah, they're really cool, and that would be fun to look at. I think in practicality, they sort of introduce some. You got to know when to use them, and sometimes the linearity, the sequential strictness of them can be a little limiting, and not give the best ergonomics if you like use them for a library. But anyway, we'll talk about what those are.
A couple of cases, like I think Zio sequels use them well, but yeah, I think it's very easy to overuse them.
Tricky. But yeah, I think there's one last question coming in. Question about Zymposium. Are there plans to do UI again? Yes, totally. We will get back to some full stack appery soon enough. That's definitely, I want to do more of that. I've been working on some things and we can show off some things. Yeah, absolutely. I don't really have much else to say beyond that. I really want to do that. I think someone previously mentioned somewhere about wanting to see sort of more full stack examples, more real world app like examples using the Zio ecosystem, and making them full stack would be splendid. That could be something that we do.
Yeah, it would be fun to kind of think about like what a really full app is, because it's one of those tough things where like I feel like there are like a bunch of things. I mean, I think there's especially you've done a bunch of them that are closer to being full, but I don't know if there's like one that's like both like kind of everything that like someone would like theoretically want to see, and they're like fully integrated example, and also just like a public thing versus like it's been done at like a bunch of companies, but like you can't like just like see their code bases. So yeah, it could be interesting to kind of think through what that is, and maybe we can have like an extended series and work towards building that.
Yeah, I think that would need some more upfront planning. If anyone has any great ideas, we can make a startup out of it. Make some money, turn this into a business. I'm a unicorn.
Have a pet store, right?
Exactly, a pet store. All right. Well, thank you for the question. Oh yeah, and also Zia streams. Yeah, we definitely need to talk about Zia
streams would be a great one. Yeah.
Because those are very cool and very powerful.
Yeah.
And can be tricky. There's a lot more complexity with streaming. That whole temporal aspect.
Yeah, and keep the questions and ideas coming. Love the interactivity.
Yep. Yeah. Leave comments in our comment box, just there in the Discord. And thanks everybody for coming. I think with questions we made it to our usual hour 30 on the dot. See you next week, everybody.
Bye.
Take care.